Hello students, welcome to the lecture of Structure of Atom. Today we will study about the Bohr's model. In the last lecture, we had seen the statements of two postulates of the Bohr's model. Today we will study them in the details and we will read about more postulates and the applications of Bohr's model. So, we had studied about these some important formulas regarding the Bohr's model. One was the Coulombic force Fe equal to kq1 q2 by r square. This formula is required to measure the force of attraction between the electrons and the nucleus of the atom. And the second one is the centrifugal force FCF equal to mv square by r. This quantity measures the centrifugal force which is directed towards the outer side of the orbit, that is away from the nucleus. So, the force of attraction between the electron and the nucleus is directed towards the nucleus. And the centrifugal force is directed away from the nucleus. These two forces makes the electron stable in the orbit, that is, the path of the electron does not change due to the balance of Coulombic force and centrifugal force. The third important formula was of angular momentum, which is equal to mvr, where m is the mass of the electron, v is the velocity of the electron and r is the radius of the orbit in which the electron is revolving around the nucleus. So, we had also derived this formula. How did we derive it? We know the formula of linear momentum P, which is mv, that is the product of mass and velocity. So, similarly, angular momentum will be the product of moment of inertia and angular velocity. Moment of inertia is written as I and angular velocity is written as omega. So, angular momentum equal to I into omega, I is equal to mr square and omega equal to v by r. So, we get the formula of angular momentum as mvr. So, now we will see the postulates of Bohr's model. The first postulate of Bohr's model said, electrons in the hydrogen atom can move around the nucleus in a circular path of fixed radius and energy. Why hydrogen atom? Because we had discussed that Bohr's model is applicable only for hydrogen-like systems. Hydrogen-like systems means systems having one electron. Okay. So, Bohr's model is applicable only for single electron systems such as hydrogen, helium plus, lithium 2 plus, beryllium 3 plus, boron 4 plus, etc. Single electron species. So, the first postulate of Bohr's model says that electrons in a hydrogen-like system can move around the nucleus in a circular path of fixed radius and energy. That is, if this is the nucleus and these are the orbits, that is, orbits are the concentric circles around the nucleus. Concentric circles around the nucleus. That is, for each of these circles, the nucleus will act as the center. And these orbits or these circular paths will have fixed radius and energy. That is, their radius will not change and their energy will also not change. These paths were called as orbits or shells or stationary states or allowed energy states. We know that they are called orbits or shells. But why stationary states? They are called stationary states because the energy remains constant or the energy remains stationary, and the electrons in these orbits are also stationary. That is, they do not show any change of energy, and they are called allowed energy states because electrons cannot move in any random orbit. These orbits should be of certain specific value, which is the allowed energy. So, electrons cannot move in orbits of any random energy value. Orbits can only have certain allowed energy values. And another point in this postulate is atom has a nucleus containing all protons and neutrons. The size of the nucleus is very small and it is present at the center of atom. So these points somewhere match with the Rutherford's model. Now the difference with the Rutherford's model comes with the second postulate, which says the energy of an electron in a particular orbit does not change with time. That is, the energy of an electron in a particular orbit remains same. This was one drawback of Rutherford's model because in Rutherford's model it was concluded that the electrons may emit energy which will lead to shrinking of the orbit. But the electrons can move from lower energy state to higher energy state by absorbing required amount of energy. Energy is emitted when electrons move from higher energy state to lower energy state. That is, if this is the nucleus and there are concentric circular paths, that is the orbits, and each of the orbits have different amount of energy. Now an electron can move from a lower orbit having less energy to a higher energy orbit by absorbing energy. Okay. We had earlier talked about the absorption spectra. Absorption spectra arises when the electrons absorb energy and move to a higher energy state. But the higher energy state is not stable. Higher energy state is unstable. So, the lower energy states are comparatively more stable. So, the electrons will gradually emit energy and reach the lower energy state. Now, the lowest energy state, which is the nearest to the nucleus, is known as the ground state. Lowest energy state is called the ground state. Ground state is most stable. and higher energy states are called excited states. Higher energy states are called excited states. So, when an electron reaches an excited state, it will emit energy and try to come back to the lower energy state. So, this is called emission, and this gives rise to the emission spectrum. Now, we will see some mathematical proofs of these statements. So, this was one statement that the energy of an electron in a particular orbit does not change with time. Bohr proved it mathematically, like if this is the nucleus and this is the orbit and here the electron is present. The Coulombic force will act in this direction. So, the Coulombic force is represented as Fe equal to K Q1 Q2 by R square. Here R is the orbit, R equal to radius of the orbit. Which orbit? The orbit in which this particular electron is revolving. Now Q1 and Q2 are the charges. Q1 is the charge of electron. What is the charge of electron? Charge of electron will be minus E, and Q2 will be the charge of nucleus equal to plus ZE. Now, if we take only the magnitudes, we can write minus E as E and ZE as ZE. So, Fe will be K E into ZE by R square, that is K ZE square by R square, and the centrifugal force will act in this direction. So, F centrifugal is equal to mv square by R. These two forces will equate each other. Fe equal to FCF. Therefore, K Q1 Q2 by R square equal to mv square by R, or K ZE square by R square equal to mv square by R. Okay. Now, if we cancel R on both sides, we get K ZE square by R equal to mv square. So, by this we can mathematically show how the two forces equate each other. Now, the next statement that we had discussed about was this transition of electrons to higher energy state by absorption of energy, and then the transition from higher energy state to lower energy state by emission of energy. So, how this can be written as? So, let's say if attraction, that is the force of attraction between the nucleus and the electron, is the Coulombic force, which is K Q1 Q2 by R square, right? So, when R is smallest, from this equation what do we see? Fe is inversely proportional to R square. That is, if R decreases, Fe will increase. That is, as the radius of the orbit decreases, the force of attraction will be greater. So, if these are the orbits, the inner circles or the inner orbits have smaller radius and the outer orbits have bigger radius. So, these smaller orbits will have greater force of attraction from the nucleus. That is, the electrons in the inner orbits or the smaller orbits will be attracted more. So, greater the force of attraction, greater will be the stability of these orbits. Greater force of attraction, greater is the stability of electrons in a particular orbit. Okay. So, the electrons in the orbit which is closest to the nucleus will have the greatest force of attraction. Electron in the innermost orbit will have greatest force of attraction. So, the innermost orbit will be most stable. Therefore, that is called the ground state. It is called ground state. Now, how are these electronic states expressed as? Electronic states are expressed as an integral multiple of a unit term. We will study the expression of these electronic states in mathematical terms in the next part. Thank you.